We're back. Now that we know all about arrays, we can actually talk about some algorithms. Specifically, we're going to talk about linear search today. Linear search, also called sequential search, occurs frequently throughout our daily lives. The concept is simple. When searching for an item or an element, start from the beginning and continue looking until you reach the end. There's no need to backtrack because you've already checked that element. You've already looked at that thing, right? Consider you're in the grocery store and you're looking for an item, right? You walk down the aisle that you suspect that it's going to be on, and you're looking for that item. There's no reason to turn around and go back because you've already covered those items. If you reach the end, then you know it's not there. Maybe it's on a different aisle, but there's no reason to backtrack. That's the important thing here. While not the most efficient searching technique, linear search still has its uses. And this video kind of explains that and explains what I'm talking about with searching through a grocery store. He actually uses the same example, which is where I stole it from. I recommend pausing this video, maybe checking out this one that's in the slides, and I'll put a link in the comments or the description below, I should say. But it's linear search, and I don't want to dive too much into it because technically we've already coded this. I'm an array helper. The contains method is probably the closest thing to linear search. We have an array that we want to search through, and we have an element that we want to search for. We have our loop, and we're starting at the beginning. We're going to go through the entire array. With each iteration, I'm asking, is the current element the one that I'm looking for? The moment that I find it, I stop my search because I have found it. Otherwise, we keep going, and we're going to go through everything, right? If I manage to go through the entire array and I never find it, we return a false value. That's because it's not there. It's not there for me to find it. So the contains method is linear search. Okay. We actually wrote several variants of this. There's contains, which I would consider a linear search. There is count, which is also performing effectively linear search, right? Instead of like stopping the moment that we find it, we ultimately count all occurrences, but this can function as a linear search, right? I talked about in other videos about how we could use count as a way to kind of mimic contains. If I go to count an element and my count that I get back is a 0, that means it's not there. Right? If I get a number that is greater than 0, that means it is there. So that can function like it contains. Lastly, index of can also function like it contains. And it is also basically linear search. Right? We have the array that we want to look through. We have what we want to look for. I'm going to start at the very beginning. I'm going to go through the end. With each iteration, I'm going to ask, is the current element the one I'm looking for? If so, I stop my search. But instead of this being a simple true or false value, we return the index. If I manage to go through the entire array and I never find it, I'm returning a -1, which indicates that it's not there. Again, this can function as it contains. This can function as a linear search. Notice in all of these, we never backtrack, right? It's exhaustive. We start at the beginning, we go to the end. We start at the beginning for a count, and we go to the end. We never backtrack. And same thing with contains. So all of these are forms of linear search, which makes, coding this a non-issue. What we really want to do is talk about it. As the name indicates, linear search operates in linear time. And then you see this crazy notation here, O parentheses N. That's going to refer to big O notation or time complexity. Big O notation, this O of N is a notation known as big O notation that is used to compare the different asymptotic runtimes or time complexities of similar algorithms. I'm going to loosely use these words interchangeably. Asymptotic runtime, time complexity, those words are very close anyway, but I may throw in big O notation when I mean one of these things. I'm going to kind of use these words interchangeably, right? Asymptotic runtime, time complexity is ultimately the same thing. Big O notation is specifically referring to this, which we'll get to in just a moment. But these are how we compare different algorithms. An algorithm, if you recall, is like a recipe. It's a step-by-step process in order to use a task. You've written several algorithms before. Maybe you just didn't recognize that you were doing it. Basically, every program that we have written is ultimately an algorithm, right? It's a step-by-step process used to perform a task. So let's take a look. For instance, there are several algorithms that can accomplish the task of sorting. This used to be part of this course where we talked about sorting in detail. We actually coded several different sorting algorithms. Now they've condensed it. We're only looking at searching algorithms, but the idea is the same. There's a lot more sorting algorithms than there are searching algorithms. And when we're talking about sorting, it is putting an array of elements in order. Be it ascending or descending, doesn't matter. It would just be in order, right? If we're talking about integers, they may be ascending, meaning they are increasing as you go through the array of elements. However, some sorting algorithms are just simply more efficient than others as they make less comparisons. And notice that comparisons is color-coded here. That's because we ultimately care about comparisons made and not time elapsed, because time elapsed can be misleading due to differences in software and hardware. Right? I'm not saying anything about speed. Right? We're using these fancy words: asymptotic runtime, time complexity. But we're not talking about speed. We're talking about efficiency. That is ultimately because speed, time elapsed, is not a good way to measure the performance of an algorithm. Okay, why? Well, there can be hardware differences. I think this one is going to be more noticeable to people. If I run contains on my computer, it may just be faster than running contains on your computer if we were to measure the time elapsed. How would I even go about doing this? Well, let's say that I have an array and I want to know, does my array contain a 7? Right, so here is a call to contains. This is just yellow because we're not printing the result, but I could, right? We could just do an S out on this. This is what I mean. So we're going to make a call to contains. I can basically time how long this takes. How? Well, I could, do essentially a stopwatch style. I could get the time, get a start time right here, and then I can get a stop time after the fact, and then calculate how much time has elapsed. And so that will tell me the speed at which this does this, right? And if you do this on your computer and I do it on my computer, we could get different times. Even though it is the exact same array of elements, it is the exact same number that we are looking for, and that could be due to hardware differences. This slide also talks about software differences, right? That is because maybe even if we had the exact same hardware, you're running some programs in the background, or I'm running some programs in the background, right? There are other things that are taking up processing power. These things combined, it's too many variables to test in an environment. So time elapsed is not a good measure. I mean, and besides, even if we could create the exact same environment, right? Let's say the exact same hardware, the exact same software. All of this lines up and it is two different machines, but the exact same environment. That still doesn't account for changes over time, meaning like if it's 1950 and I am doing identical setups versus if it's 2050 and I'm doing identical setups, the algorithm is essentially the same, but there's been hardware changes over time. So time elapsed is just not a good measure for how good, how fast, ultimately, an algorithm is. What we care about is number of comparisons made, because that is a true test to efficiency. We'll look at what a comparison actually is in just a moment with our linear search. So the time complexity of an algorithm should be discussed in regard of the best case, worst case, and average case scenarios. So we'll break this down as well. But when we talk about an algorithm, we care about a best case scenario, an average case, what usually happens, and the worst case. And notice that we use different symbols to denote what notation we're dealing with. So the notation big O of n means that linear search will perform n comparisons in the worst case where n is the number of elements. That's not technically what this means, but I find this is the best way to describe it to students and they understand it. In the worst case, linear search is going to make n comparisons where n is the number of elements. What this technically means is that as the array gets larger, how does the number of comparisons change in the worst case? It's going to grow linearly. Okay, let's talk about these comparisons. Let's actually look at some things. Let's look at the worst case for linear search. Let's say that I have this array and I want to search for 7 using linear search. Just a quick glance, you see that 7 is the last element. But you should know from working with contains, working with count, working with index of, that whenever we go to search for this thing, we got to start at the very beginning and we're going to work our way towards the end, right? So we're going to look at the very first element and ask, is this the one I'm looking for? No. That's a comparison, right? I just compared 13 to 7. We would move on to the next element and ask, is this 7? No. I want to make another comparison. We'll look at the next element and ask, is this 7? Nah. I've made a third comparison. And lastly, we would look at this last element and ask, is this 7? Oh yeah, we found it. We were successful, but notice on this last iteration, I compared the current element to the one that I'm looking for. That is a comparison. We made 4 comparisons and our length is 4, right? This has 4 elements in it. Okay, so that is one way to think of this big O notation. I went in the wrong direction. So we made n comparisons, and that was a worst case scenario. It was a worst case because the element we were looking for was the last element. Now, technically what this means is that as the array gets bigger, right, as the number of elements gets bigger, how do the number of comparisons increase in the worst case? If I add one more element to this array, the number of comparisons, let's say I tack it on the beginning, right? If I add one more element to this array, I increased by 1, I would also add 1 comparison. That's what it actually means. That is what this, this linear time complexity, asymptotic runtime actually means. Because we're talking about the worst case scenario, how do the number of comparisons change? Okay, now that was a worst case scenario. Linear search, actually, there's multiple worst case scenarios. I want you to think for a moment what the other one is, but a worst case scenario is what we saw here, where the element I was looking for was the last element. I had to look through the entire thing in order to find it. Another worst case scenario is, what if the element I'm looking for is not even in the array? Let's say that I'm searching for 12. Right? I'm going to ask, is this 12? No. That's a comparison. Is this 12? Nope. That's another comparison. Is this 12? No. Is this 12? No. Notice that I made 4 comparisons and I still didn't find 12. That is equal to when we were looking for 7, right? So this is also a worst case scenario. That is a big O of n. We made the number of comparisons we made is equal to the length, but technically what it means is if I were to add one more element, the number of comparisons would increase linearly in the worst case. So that is worst case. And I think those are really good examples, right? The worst case is if the element we're looking for is the last element or it's not even there. So what is the best case scenario? With that in mind, what is the best case scenario for linear search? What does it look like? How many comparisons are we going to make in the best case? Our answer here is 1. Linear search is going to be omega of 1 in the best case scenario, as only 1 comparison has to be made. I'm going to search for 7 in this array. Is this 7? That's a comparison. And yeah, I found it. This is best case scenario. The element I'm looking for is literally the first one I checked. Okay. So it looks like I make 1 comparison. What this technically means is that the number of comparisons is constant, meaning the best case scenario doesn't really change. As the array gets bigger, the best case scenario is still the same. The element that I look for is the first element. That is technically what this means. But if it helps you think about this as you make one comparison, that's fine with me. Okay, it is not the number of comparisons made. It is technically, as the array gets bigger, how does the best case scenario change? How does the number of comparisons change? And then the number of comparisons doesn't change. The number of comparisons remains constant. Keep that word in your mind when we talk about this, about constant. We'll come back to that. So with that in mind, how many comparisons does linear search make on average? On average, it should be, if the best case is at the very beginning and the worst case is at the very end, on average, it's somewhere in the middle. On average, we're going to do half of the array, right? If n is the number of elements, I'm going to look through about half of them on average in order to find my element. So here is our asymptotic runtimes for linear search laid out, right? Our best case scenario is constant. That is, we make one comparison. We look at the first element and then we find it. Our worst case scenario is it's the last element in the array, or it's not in the array at all. And then our average case is it's somewhere in the middle. Okay. So I like to tell students to think about these as number of comparisons made. In our best case, we only make one comparison. In our worst case, we have to look at every element in the array. In our average case, we have to go through half of them. Now, technically, that's not what these mean, but I find that that's the best way for students to think about them. Here are some other common time complexity notations, and we're going to assign names to these, right? We have seen this one, and we have seen this one now. We would call this first one constant, right? I used that word earlier. Linear, we saw this with linear search. Quadratic, there's a lot of sorting algorithms that are in this area. Logarithmic, linear logarithmic, and then exponential. These are also sorted, right? And best efficiency, like constant, is insane. You really, really want that. And exponential, I can't think of an algorithm off the top of my head that is exponential that is used, right? Like I said, a lot of our sorting algorithms are in this range, in this area. Now, you'll notice that I'm using big O here, and we talk about big O, right? I first introduced this by referring to big O notation. As it turns out, that's the one we care the most about. You may think that we care about an algorithm's performance in the average case, right? Because that's the one that happens most often. But we care about the worst case because this is the one that is going to upset people, right? If I'm at your website and you have a table, right? Let's say you're at Wikipedia and there's a table of data there and you want to sort it. And so you tell it to sort. And it happens to be a worst case scenario. So you got to wait for that sort to finish before the data is in the order that you want. It may take so long that you're like, I don't want to deal with this anymore. And you leave Wikipedia, you leave the website. That's kind of the idea here. We care the most about the worst case scenario because if the worst case scenario happens, that is what causes people to abandon the actual algorithm, right? And think about this for a moment. Worst case actually happens frequently. Despite an average case, despite this word average, that doesn't necessarily mean it is the most frequent case to happen. Okay, how can I prove this? Think about when we were searching for 12. Okay, I have an array with only 4 elements, with only 4 integers. If you were looking for any number that's not these 4, you're in worst case territory. Now, our linear search is going to be relatively fast. It's still only a big O of n. In comparisons is quick in the grand scheme of things because, as I said, our sorting algorithms can be n squared in terms of efficiency. But there are infinite numbers that we could search for outside of these 4 that would not be in the array, which means we're in worst case territory. So worst case scenario doesn't mean that it is infrequent, or rather average case doesn't mean that this happens most frequently. It's just the average case, right? It could be worst case scenario happens quite frequently. And so this is what we care about. This is why the term big O notation gets used, even though there's other scenarios. Okay. That is going to wrap it up for our discussion on linear search and our introduction to time complexity. I'll see you in the next one.